Okay, so let's recall what we have been doing so far. Our eventual aim is to describe scattering of particles and tell what happens in future after these particles have interacted. And towards that goal, we have been trying to figure out S matrix elements, which are basically the inner products of in and out states, and we had made significant progress in that direction and found that we can write S matrix element, which we write as S of this P 1 to P n and K 1 to K n K m. So, in general m and n will be different. Okay. We showed that this is equal to I over square root of z, and you have m plus n such factors, m such factors, okay, and then you have integral d4 x 1 to d4 x m, then f of k 1 x 1 times f of k 2 x 2 and so forth to f of k m x m, okay, times box 1 plus m p square. Okay. This is basically del mu, where the derivative is with respect to x 1. Okay. So, and then other factors, box m plus m p square, okay, times P 1 to P n, that is the out state, then time order product of these fields phi at x 1, phi at x 2, so and so forth, phi at x m, and here you have the vacuum. Okay. We could write our expression in terms of fields phi and could completely get rid of the in state, and instead we have now vacuum. Now, if you were to repeat similar steps for the out state, this one here, okay, then you are going to get the following, and that is something you should check. So, you are going to get, in addition to this factor I over square root of z to the m, you are going to get n such factors also. So, you will get this. Then you are going to get f of P 1 x 1, but this time it will be a complex conjugate. P n x n and a complex conjugation here, times you will have these differential operators also for just like you have box 1 plus m p square. Let me put a label x here, because now we have both. Sorry, I made a small mistake. So, here you will have corresponding integration variables, which we will write as d 4 y 1, d 4 y n, and these will have arguments y 1 to y n, and these derivatives, which are with respect to x 1 and x 2 and so forth, I will explicitly write them as box with subscript x 1 and this one is box with subscript x m. Okay. Meaning this differential operator del mu, this del mu is basically del. So, this is this, that is the box. So, here it is del over del x m mu. Okay. This is the derivative operator here. So, that is what we have in here, and when we are getting rid of this out state, we will have just like these differential operators, we will have box y 1 plus m p square. So, now this box which is again del mu, the derivative is with respect to y 1 mu. Okay. And we have several of them up to box y n plus m p square, and of course, this will get changed to, let me, so this I will erase, and let us see whether I can erase. And then what will you have? We had time order product of fields where the number of fields was equal to the number of labels k 1, the number of labels we had in the in state, which was m labels. But now we are going to get, in addition to those, n more fields coming from the out state, and we will have this time order product of phi x 1 up to phi x m that we already had, and now we will also have phi of y 1 to phi of y n, okay, and we will have this vacuum expectation value of this time order product. Okay, so, this is our LHZ reduction formula. And we have missed these factors of here we had square root of 2 omega k 1 for x 1 and similarly for other variables. So, I should multiply this somewhere how should I write here, 2 omega k I product I equal to 1 to m times j equal to 1 to n 2 omega k j. Okay. So, this also should be multiplied. So, I will put a cross here, so that equation starts from this place. I am sorry that this is not looking so nice, but this is what it is. Okay. So, that is our LHZ reduction formula. Now, you see that these objects, this vacuum expectation value of this time order product, that is what is a green function is, right. We have talked in detail about this and perturbative expansion of this object in the previous course, part 1 of this lecture on quantum field theory, and you may recall that we can also write this using momentum space variables. Okay. So, and we saw perturbation expansion of this, how to draw Feynman diagrams. This is what led us to Feynman diagrams. Okay, and you should you go back to the previous course and see what we learned about all this, but I am not going to go back to that discussion, and I will assume that you already know what these objects are, okay, and I am going to proceed with that. Okay. So, let me just write down here, these are our correlation functions or Green's functions. Okay, this is what we used to call, this one will be G n plus m x1 to x m, then y1 to y n. Okay. That was the notation which we used last time, a bit standard notation actually. So, now my plan is to further manipulate this and put it in a nice form. Yeah. And before I do that, I will also just remind you what f of k is. This was 1 over 2 pi 3 over 2, and then you had 1 over 2 omega k in the square root. Okay, that was the definition. So, you see here that you have, let us look at x variables, let us look at x1. Okay. You have d4 x1, okay, that is the measure. Then you have fk of x1. Now, in fk of x1, if you look at the expression here fk of x, the dependence on x is fairly simple, okay, or this is just e to the minus I k dot x. Okay. This thing is also, you can write this as minus I k dot x, which is k mu x mu, and 0th component is omega k, that is the energy. Okay. So, as far as x dependency is concerned in f k, that is simple, that is an exponential. Okay. Integrating d4, integrating this exponential over this variable x1, that is simple. Okay. That will give you a delta function. The only problem is that you have this differential operator acting on this Green's function, which is also a function of x1. Okay. But what I am going to do is turn this into a simple expression, so that I can integrate easily over x1 and x2 and so forth. And the idea is that instead of working with this Green's function in the coordinate space, okay, I will go to Fourier space. Okay. So, I will Fourier transform these variables, this function with respect to these variables. Okay. And once I Fourier transform, the x dependence will become simple, it will be a simple exponential function. Okay. Then taking this derivative operator and acting on a simple exponential function is easy, it will give you back the that exponential function times some constants, and then I can just integrate out over x1 or any of the xi's or yi's. Okay. So, that is the plan. Okay. And the reason being simple, because if I go to Fourier space, the x dependence trivially factors out as an exponential. Okay. And that is why I am going to go to Fourier space. So, let us see what happens when we do that. Okay. Good. So, I will define the Fourier transform. So, let us define G tilde. So, let us say I have some number of a function G tilde which depends on okay, let me first write, then I will say it will be easier. Okay. So, I am defining the Fourier transform of G tilde of x1 x2 so on and so forth up to xs. So, G tilde of S K S is defined to be d4 x 1 e to the minus I k 1 dot x 1, okay, integral d4 x 2 e to the minus I k 2 dot x 2, so and so forth, integral d4 x s e to the minus I k s dot x s time, and this Fourier transform is being done on G s x 1 to x s. Okay. So, given a correlation function or a Green's function, okay, which is a function of these x 1 to x s coordinates, I do a Fourier transform of each of these. I do a Fourier transform, a multidimensional Fourier transform, okay, and the conjugate variables corresponding to x 1 to x s are k 1 to k s, and that is the general Fourier transform that you will write, okay, which is same as d 4 x 1 to d 4 x s times e to the minus I k 1 x 1 plus so and so forth k x dot x s k 1 dot x, okay, acting on G s x 1 to x s. Now, you see, this is what I was saying. If I now write G s x 1 to x s in terms of G tilde, okay, where it depends on these conjugate variables k 1 to k s, then the x dependence will be simple. So, I invert this and write G s, okay, I am just writing the inverse Fourier transform now. This is d 4 k 1 over 2 pi to the 4, so and so forth, d 4 k s over 2 pi to the 4, then you have e to the plus I k 1 dot x 1, so and so forth, k s dot x s times G tilde s k 1 to k s. Okay. So, you see now, if I go back and substitute in here, this is G, okay, substitute in this expression the Fourier transform, or not the Fourier transform, but this expression, okay, where G tilde s is the Fourier transform of G s, then the x dependence is simple, it is of the exponential form. Okay. So, that is what I want to do. And another thing is that, just a second. I think I had written here itself. Yeah. And another thing is that these differential operators act simply on the exponentials. Okay. So, for this thing, let us call this as g n plus m, okay, and these variables, and I do the similar thing. So, I will have all these exponentials both with x and y, and then I take derivatives. So, let us look at first this one, box x 1 plus m p square acting on the x dependence coming from here. Okay. So, if you do so, let us look at box x 1 plus m p square acting on g m plus n, and then you have x m and y 1 to y n. Okay. This will give you what? This will give you back apart from, see, all these integrals are still there. I will not write them in full, but you have all these integrals. Okay. Then this exponential will give you k1 minus k1 square plus mp square times again the same exponential times g tilde. Okay, why? Because the box x1 is basically del mu, right, with respect to x1 variable. So, when this acts del mu acts on e to the I k1 dot x1, it pulls down I k1 mu. Then you again act with another del mu, it again pulls out I k1 mu. Okay. One mu will be up, one mu will be down, and I times I gives you a minus 1, and k mu is k square. So, you get minus k square plus mp square, okay, when you take this the differential operator and act on g. So, if you do this same thing for each of the coordinates x, all of these x coordinates and all of the y coordinates, then you will get the following result. So, instead of writing that, let me just collect all the terms. So, what I will do is, okay, I will write one more time this thing. Okay, let's write it again. It will be easier to see what is coming from where that way. So, S of P1 to Pn, K1 to Km, okay, is equal to I over square root of z m plus n, then d4x1, d4xm, d4xy1, d4yn, then you have the f case, f k m x m, okay, times f p 1 y 1 to f p n y n, then all these differential operators, okay, I will write it in the following manner. So, the variables which I will use is when I am transforming this g. So, corresponding to x 1, I will write k 1 prime, okay, and for x m I will write k m prime, and for y 1 I will write p 1 prime, and y n I am saying about the conjugate variables. Okay. For y n I will write p n prime. So, you will get the following, this times d 4 k 1 prime over 2 pi to the 4, d 4 k m prime over 2 pi to the 4. Okay. This is coming from here, right. I am substituting g in this expression, this one, this g in terms of Fourier transform, and this brings these integration measures. Okay. I am just putting a label prime on this, that is all I am doing. And then similarly for the y 1 to y m, I will have d 4 p 1 prime, d 4 p n prime over 2 pi to the 4, okay. And then these exponentials, okay. So, you will have e to the, let me write here, e to the I summation over I k I prime dot x I, or if you wish, let me write it like this: k1 x1 k1 prime x1 plus so and so forth km prime xm prime xm, okay, and then you have e to the I p1 prime dot y1 pn prime dot yn, and then finally g tilde, that is the Fourier transform, and the arguments are k1 prime to km prime, p1 prime to pn prime. Okay. Did we miss something? Yes, we did, and that is these differential operators, right. I have written everything else except for these differential operators. Now, when these differential operators act on the g, they pull out these factors, such factors, right, minus k1 square plus mp square minus k2 square plus mp square. So, that is what is left, and I should write here minus k1 square plus mp square minus km square plus mp square times minus, and that is prime, okay, k1 prime km prime minus p1 prime square plus mp square so and so forth minus p n prime square plus mp square, and again I have forgotten to write down 2 omega k 1 2 omega k m square root of 2 omega k m, then square root of 2 omega p 1 p n. Okay. So, that is the result when you express things in terms of g tilde. Okay. Good. Now let us settle x integral, okay, and then y integral, of course, and that is easy. Remember, let us see where all the x dependence is. So, x dependence is in here, then in here. These are the only two places where you have x dependence. Okay. So, let us write down what you get for d4 x1. Okay. So, you will get integral d4 x1, then you get e to the, what was it, e to the minus I k dot x. Okay. So, f k x1 is e to the minus I k1 dot x1. Okay, just a second. Is this correct? F k x1, f k x, let us check. Toolbar, no, not this. I want to see what is the expression of f k of x1. Okay, anyhow, I will check the sign and then I will tell you in the next video, but let me tell you what I was about to do or what I am going to do. There is some discrepancy in sign compared to my notes, but let us proceed anyway. So, this will have 1 over 2 pi 3 halves and 2 omega k 1, okay, that is f k 1 x 1, and then you have another x dependence coming from here times e to the I k 1 dot x 1, k 1 prime dot x 1. Okay. That is all for x 1. Now, this one you can integrate out and it will give you 1 over 2 pi 3 halves 1 over 2 omega k 1, okay, and this exponential, this will give you integral over upon integrating it will give you 2 pi to the 4 delta 4 of minus k 1 plus k 1 prime. Okay, that is what you will get, and pending this issue of sign which I am facing, you are going to get this, that is the delta function you are going to get. Okay. And then similarly, you will get for each of the x variables and also for the y variables. Okay. And once you have gotten a delta function, integrating over k 1 prime and k 2 prime and p 1 prime and p 2 prime, that will be easy. So, that will be the next step. Okay. But before I do that, I want to check my sign and then we will continue in the next video. Okay, so I checked and I do not find any problem with signs actually. So, this is fine, let us proceed. So, I was doing the x integral. Okay, just a second. Yeah. So, I have collected all the factors which contain x 1, okay, and the result is that you have an integral over d 4 x 1 e to the minus I k 1 dot x 1 over this factor coming from f k 1, this is what I wrote, and then you have this exponential coming from here e to the I k 1 prime dot x 1. Okay. So, you will get these factors which are in the denominator, and when you integrate over x 1 you generate a delta function with the factor of 2 pi to the 4. So, that is 2 pi to the 4 delta 4 and k 1 prime minus k 1, okay, which means that this delta function hits only when k 1 prime is equal to k 1. Okay. So, this dummy variable k 1 prime, when it equals the variable k 1, which is what is present in this S matrix element, then it contributes, otherwise its contribution is 0. Okay. And as you can see that you will get similar factors for each of the xi. So, each of yeah, okay. So, for example, for x 2 I will have exactly the same thing with omega k 1 replaced by omega k 2, and this will have delta 4 minus k 2 plus k 2 prime. Okay. So, that is one thing. So, we have taken care of integrals over x 1. So, I will write down on the next sheet. Just a second. Yeah. So, each of the, or rather integrating over xi gives 1 over 2 pi 3 halves times 1 over 2 omega ki and the square roots, and then you have this vector 2 pi to the 4 delta 4. I will write it as k1 prime minus k1. Okay. These are 4 vectors. Now let us look at y integrals. Integration over y I. Let us go back. So here you have, okay, there is again a small mistake here. So I should show you that we had the P1s, FP1, they had a complex conjugation, which is what is missing here. So I will put this complex conjugation here. Okay. Now, because of complex conjugation, FP1 would have, instead of e to the minus IP1 dot x y1, it will have e to the IP1 dot y1. Okay. That's the difference with respect to the previous case, for the case of x1. Okay. This sign, instead of being minus, will be a plus. Okay. Other factors are going to be the same, and then you have e to the I p1 prime dot y1. Okay. So the sign of this factor in the case of y1 doesn't change. So what we get is, there will be a change of sign here. So instead of minus p1 here, we will have p1. Okay. So for y1, I will get 1 over 2 pi 3 halves, 1 over 2 omega p1 in the square roots, and then 2 pi to the 4 delta 4 minus p1 plus p1 prime. That's what you are going to get. Okay. So you will get 1 over 2 pi 3 halves, and then okay, I have changed the this nib of this pen, and I think I should make it bolder. Brush library. Yeah. Let's hope this is better. Okay. Then 2 pi to the 4 delta 4, and then we have, sorry, here it should have been I, pi prime plus pi. Okay. Which means when pi prime is equal to minus pi, okay, then this delta function hits. Okay. And this delta function hits when ki prime is equal to ki. Okay. So now we can substitute all this into our formula for the S matrix and obtain the following. So what happens, we'll have these factors, okay, I over square root of z m plus n, then you have all these root 2 omega ki, but then that root 2 omega ki okay, that will get cancelled. See, each of these fki, they are bringing a factor of 1 over root 2 omega ki. Okay. So that gets cancelled with this root 2 omega ki because of the normalizations that we chose, okay, which brought these factors. So each of these root 2 omega ki's are going to disappear. There will be no square root of 2 omega ki in this. Okay. Then all the x and y integrals are gone. These f's are gone. Okay. Integral over d4k1, they will be left. Okay. And then of course these objects are there. So let me write down and then let's check. Maybe on the next sheet. So I have found that S P1 to P n and then K1 to Km, okay, that is equal to square root of z m plus n, okay. Then we will have each of these x integrals brings 1 over 2 pi 3/2, okay. So we will have m such factors coming from xi integrals and n such factors coming from pi integrals, okay. So let me keep that. Okay, so I have taken care of these 2 pi 3/2 and also these square root of 2 omega ki's, or rather from here I should be looking here, this have been taken care of. Now I will have 2 pi to the 4 times these delta functions coming, okay, and I should take this and see these 2 pi to the 4, okay, let me go slow. So here look at, so these factors have been taken care of. Now let's look at this. I will integrate over this over d4 k1 prime, okay. So look at this, this has d4 k1 prime over 2 pi to the 4, so that 2 pi to the 4 cancels this one, okay, and you are left with only this delta function. So you have d4 k1 prime times the delta function, okay, and then the k1 prime appears here in this factor, minus k1 prime square plus mp square, okay, and then the other place is here g tilde m plus n, okay, here k1 prime. So what I should do is, all the 2 pi factors are gone, all I have to do is turn k1 prime into k1, okay, because that's what this delta function does. So here I will have minus k1 square plus mp square instead of minus k1 prime square plus mp square. Here it will be, this is anyway already taken care of, this will become k1, okay. And when I do for p1, I should again the same thing, all these 2 pi to the 4 factors are gone, but this time the delta function is p1 prime is equal to the delta function forces p1 prime to be equal to minus p1. So what will happen is, here instead of p1 prime I will have minus p1. So these first m labels get changed to k1, k2, so and so forth km, and these n labels get changed to minus p1, minus p2, so and so forth to minus pn. Okay, so that's the replacement that we need to make. So I'm going to write this result. This is fine. Then I have product of, did I write like that? No. So I will write it as let's go back, what was that? Minus k1 square plus mp square. So minus k1 square plus mp square times other terms, and the last term is, last factor is km square plus mp square, okay. Then I have minus p1 prime square plus mp square, but p1 prime I should replace by minus p1, but when I square it, of course the sign change doesn't matter, so I get minus p1 square plus mp square, so and so forth, and the last factor is minus p n square plus mp square. Okay, then what is left is g tilde, and here you will have k1 up to km, and then minus p1 up to minus pn. Okay, where remember that these energies p1 pi0 is same as, okay, pi, the zeroth component of p is just the energy which is okay, and similarly for ki0. Okay, that's the constraint you have on these momenta, 4 momenta. Okay, so this is all good. Okay, not here, I mean, sorry, this I should not put, it continues in the next line. Okay, so now let's look at these factors. Okay, so if it looks like when my when these momenta p1 to pn and k1 to km, they are on shell. Okay, on shell meaning they satisfy, let's say for k1 square is mp square. Okay, that's the condition of being on shell. Then this factor is 0. Okay, similarly all these factors will be 0 when the corresponding momenta are on shell. Okay, so looks like that the S matrix is 0 for that, which of course it cannot be true, that there is no transition probability, the transition probability from in state with all these momenta to an out state with all the pi's is 0. Okay, that cannot happen, because of course you know that scattering will happen. So clearly these zeros, okay, they should be killed by some poles coming from here. Okay, that's the only way you can save this, otherwise it will not work. Okay, otherwise it will give you 0. So the way it works is the following. Okay, I'll prove it in detail later, but I'll tell you what happens. If you look at a 2-point function in an interacting theory, okay, let's say there is momentum k1, okay, then this 2-point function, which of course has all these diagrams in there, okay, which we have done previously. Let me draw a few. So for example, this is this plus this. I'm just drawing in 5-4 theory, this and many other diagrams, infinite of them. Okay, these are all diagrams which have only 2 external points, this and this. And when you look at this function, when you look at this 2-point Green's function, okay, then its behavior is given by this. Let's call it k not k1 plus other terms. That doesn't bother right now. That doesn't bother us right now. So thing is that, see, if k square is very close to the physical mass squared, meaning if the momentum is close to being on shell, then the claim is that the leading behavior of this 2-point function is given by this term. Other terms are not that singular, meaning you have a pole in the 2-point function, okay, and pole is at the physical mass, right? So if you are looking at this object in the k square plane, okay, so if you are looking at the complex plane of k square, okay, then there is a pole at the physical mass. So whatever that physical mass of particles is, okay, there is a pole here, okay. So this is the dominant behavior, and this is what is going to save us, that actually these poles will get cancelled against these zeros which you see here, okay, and I will show you in the next video how that happens. But for now we will, this I will assume, okay, and later in the video, after once we have done this S matrix formula completely, I will show you how to obtain this result explicitly. Okay, so see you in the next video.